have talked about vectors and scalars, we have talked about vector space, and we have talked about vector products. Now, the next topic that will be the topic for today's lecture will be linear dependence, basis and dimensionality. So, what is linear independence? So, vectors are said to be linearly independent if one cannot be expressed as a linear combination of the others. So, if you take a set of vectors, okay, then you say that if you can express one as a combination of the others, then you say that they are linearly dependent, and if you cannot do that, you say that they are linearly independent. So, formally the way you define linear independence is that if you have a set of vectors v1, v2, v3 up to vn, okay, you say that these vectors are linearly independent if the statement c1 v1 plus c2 v2 plus up to cn vn equal to 0 is only valid when c1 equal to c2 equal to c3 equal to cn equal to 0. So, c1, c2 etc. are real numbers, okay, c1, c2 up to cn, these are real numbers, okay, and this is always true whenever you have c1 equal to c2 equal to c3 and up to cn equal to 0, then this first relation will hold. So, this first relation holds whenever the second relation holds, okay. So, the second relation implies the first, okay, but if the vectors are linearly independent, then there is no other solution. There is no solution with non-zero c1, c2 with any one of one or more of these not equal to 0. So, that is what it means to say that the vectors are linearly independent. Okay. So, again the formal way of stating is that if you have a statement like c1 v1 plus c2 v2 plus c3 v3 up to cn vn equal to 0, that necessarily implies c1 equal to c2 equal to c3 up to cn equal to 0 if the vectors are linearly independent. If they are linearly dependent, you can have another set of c1s where all of them are not 0, which still satisfy the first equation. Okay. So, another way, now suppose you have a set, suppose we find equation 1 satisfied for c1 not equal to 0. So, you find c1 not equal to 0 and maybe some of the others are also not equal to 0, okay. Maybe some of the others are also not equal to 0. So, if you find equation 1 satisfied for let us say c1 not equal to 0, then I can take v1 to the other side, okay, and I can write it as the following. I can write v1 is equal to c2 and I can divide by c1 because it is not equal to 0, c1 minus c3 by c1 v3 and so on, minus cn by c1 vn. Okay. Why I am writing this is that c2 by c1 is now a real number, as is c3 by c1 and so on. So, what I did is I wrote v1 as a combination, as a linear combination. So, this is called a linear combination where you multiply each vector by a real number and you add them up. So, I wrote v1 as a linear combination of v2, v3 up to vn. So, whenever you have vectors that are not linearly, this is a case when they are linearly dependent. Okay. So, when vectors are linearly independent, then you can write one as a linear combination of the other, which is the same as this formal statement of linear independence. Okay. So, just to emphasize again, we said that these vectors v1, v2, v3 up to vn are linearly independent if the first equation implies the second. Okay. So, now in any vector space, okay, there are always a maximum number of vectors that are linearly independent, okay, and we will come to that in a minute, okay. But let us take an example. Suppose we take the usual 3-dimensional vector space, okay. Now, if you take vectors, let us say if you take any two vectors, let us say a and b, okay. So, if you take two vectors, then you ask what is the condition that these vectors are linearly independent. Now, A will have certain components, let us say Ax, Ay, Az, and B has components Bx, By, Bz. Okay. Now, A and Y being linearly independent means you will write that you will write say C1A plus C2B equal to. So, you check if they are linearly independent, then this is satisfied by some C1 and C2 which are both not 0. Okay. So, if this is satisfied for some C1 and C2 which is not 0, then I can write A as minus C2 by C1 B. Okay. So, that means A is proportional to B. Okay. So, A is a vector that is in the same direction as B, it has a slightly different length. So, if you take two vectors, then when you say that they are linearly dependent, that means they are proportional to each other. Okay. So, if you take only two vectors, then they are linearly dependent if they are proportional to each other. Okay. So, this is the condition for two vectors. Now, what if you have three vectors? Suppose you have A, B and C. Okay. Then what we say is that the condition for linear independence is that this C1A plus C2B plus C3C equal to 0, and I should probably emphasize that this is actually a 0 vector. So, in all these cases this left hand side is a vector, so right hand side is also a vector. So, it is a 0 vector. Okay. So, this equal to 0 for some C1, C2, C3 not equal to 0. So, if they are linearly dependent, then you have some C1, C2, C3 which is not equal to 0, for which this is valid. And how do you find the C1, C2, C3? I mean how do you state this condition? So, what you will say is that if I write the x, y and z components of this, I will get three equations. So, C1 Ax plus C2 Bx plus C3 Cx equal to 0, and then I will get C1 Ay plus C2 By plus C3 Cy equal to 0, and C1 Az plus C2 Bz plus C3 Cz equal to 0. So, these are the conditions. So, you have to have some C1, C2, C3 which are not all 0, okay, satisfying these three equations. And you might remember from theory of these are all homogeneous linear equations. Okay. So, if you think of C1, C2, C3 as variables, these are homogeneous linear equations. Okay. Now, all these are satisfied for C1 equal to C2 equal to C3 equal to 0, but the condition for non-trivial solution, a solution where C1, C2, C3 are not all 0. So, that condition for existence of non-trivial solution okay. And this you might be familiar. So, we say the determinant involving Ax, Bx, Cx, Ay, By, Cy, Az, Bz, Cz, that should be equal to 0. So, the condition for existence of non-trivial solution, I will just write determinant of delta equal to 0, and what is this delta? So, delta is this matrix equal to Ax, Ay, Az, Bx, By, Bz, Cx, Cy, Cz. So, if the determinant of this matrix delta is 0, then you say A, B and C are linearly dependent. Okay. So, if this determinant is not equal to 0, then A, B, C are linearly independent. Okay. So, in this way you can there are very easy ways to check whether two or three vectors are linearly dependent or independent, okay. And you can do this for all vector spaces, you can check linear dependence or independence. Okay. Now, the maximum number of linearly independent vectors is called the basis. Okay. So, if instead of having just A, B and C, if you had a fourth vector D in 3-dimensional space, okay, then you would have 4 equations. If you had a fourth vector, okay, so if you had A, B, C and D, okay, then what you would have is you will have C1, C2, C3 and C4, and you would have 4 unknowns and 3 equations. And obviously you can always find a solution, okay, because you can always adjust the fourth variable so that it satisfies these equations. Okay. So, what I want to say is that in 3D space you can have a maximum of 3 linearly independent vectors, and we will see this in a few minutes. Okay. So, this brings us to the idea of basis and dimensionalities. So, vectors, if you have a set of vectors, okay, they form a basis for a vector space if 2 conditions. First, they should be linearly independent and they should span the entire vector space. So, suppose you had 3 vectors B1, B2 and B3, okay. These should be linearly independent. So, when you say that they should be linearly independent, we already saw the definition of linearly independent, a linear independence, and they should span the entire vector space. So, what do you mean by they should span the entire vector space? Any vector V can be written as some linear combination of B1, B2, B3. So, some linear combination. So, I will just write C1 B1 plus C2 B2 plus C3 B3. So, any vector V, any vector. So, you take any vector, you can write it as a linear combination of these 3 basis vectors. So, in 3-dimensional vector space, so one example is I, j, k, the unit vectors in the x, y and z directions. Okay, these form a basis because they are linearly independent. Okay, you can show this. For example, if you take the determinant of the components, this delta that we talked about. Okay, so if you have I, then Ax is 1, Ay and Az are 0, j for j, Bx is 0, By is 1, Bz is 0, and for k vector Cx equal to 0, Cy equal to 0, Cz equal to 1. Okay, and you can clearly see that the determinant is equal to 1 and it is not 0. So, the determinant of delta equal to 1, so it is not equal to 0. Okay, so just to write delta for this ijk, delta equal to 1 0 0 0 1 0 0 0 1 and determinant of delta not equal to 0. So, these are linearly independent and they span the entire vector space, because you know that any vector you take, so suppose you take any vector V, I can write it in terms of its components. So, Vxi y, Vyj plus Vzk. So, this vector is written as a linear combination. So, Vx, Vy, Vz are scalars. So, you wrote this vector as a linear combination of I, j and k. So, that means I, j, k span the entire space and I, j, k form a basis in this vector space. So, they are linearly independent and they span the entire vector space. So, any vector in the vector space can be written as a linear combination of I, j, k. So, that is in 3 dimensions. Okay. Now, what I said is the maximum number of linearly independent vectors, okay, is called the basis of the vector space. So, in any vector space you can have a maximum number of linearly independent vectors, okay, and that is called the dimension. Okay. So, the maximum number of linearly independent vectors is called the dimension of the vector space. Okay. So, you can ask the question what is the dimension. So, in the case of the 3D vector space, the dimension is 3 because your number of the maximum number of vectors that can be linearly independent is 3. If you have a fourth vector, it will be linearly dependent. Okay. So, the basis is also the number of vectors in the basis is also gives you the dimensionality. So, you can either say maximum number of linearly independent vectors or the number of vectors in the basis. Okay. So, both are equal to the dimensionality. So, in 3D space you have 3 basis vectors. So, the dimensionality is 3. So, let us take examples of bases. So, suppose you have in 3D space, so your I, okay, I can write that as 1 0 0, j I can write as 0 1 0, k I can write it as 0 0 1. And what is important is that these are not unique, okay. These are not the only bases that you can have other bases also. So, for example, you can have a vector, let us say b1 equal to 1 1 0, b2 equal to 1 minus 1 0, and b3 equal to 0 0 1. So, this is also a basis for 3D vector space. Okay. So, the basis is not unique, you can have many different bases, but they should still satisfy the conditions that they should be linearly independent, and you can write any vector as a linear combination of these, okay, and you can verify that you can write any vector as a linear combination of these linearly independent vectors. Okay. So, for example, suppose you just take two of these vectors b1 and b2, okay. Now, these are b1 and b2 are linearly independent, okay, but I cannot express an arbitrary vector as a linear combination of b1 and b2, because whatever linear combination I take of b1 and b2, the z component will always be 0. Okay. So, just b1 and b2 cannot form a basis, you need b1, b2 and b3 to form a basis. So, you need the 3 vectors to form the basis, and what we said again is that the number of vectors in the basis is called the dimensionality. So, this is so the dimensionality of 3D space by definition equal to 3. Okay. So, this is a formal definition of dimensionality, okay, and that is why we call it 3D space. Okay. Now, in the last class I talked about the vector space of functions. Of functions of x. So, I said that if you take the space of all functions, okay, then that is also a vector space, and what is the dimensionality of that vector space? So, vector space of functions, okay, so this f of x, okay. So, if you want to write an arbitrary f of x as a linear combination of certain number of f of x, okay, because the space of functions is infinite, you can have infinitely many different functions, okay. So, actually the dimensions of this vector space of functions is infinity. So, dimensionality equal to infinite. Okay. 3D vector space of course has dimensionality of 3, and vector space of functions has dimensionality of infinity. So, now you can look at some other vector spaces. Okay. So, for example, you can consider a vector space. So, we said that so we consider the vector space of polynomials up to degree, let us say 2. Okay. So, that will be of the form a0 plus a1x plus a2x square. Okay. So, that is what a typical polynomial will look like. Now, what is the basis for this vector space? Okay. And you can convince yourself that basis, one choice of the basis equal to 1 x square. Okay, that is the obvious choice of basis, because any polynomial of degree 2 I can write as something into 1 plus something into x plus something into x square. So, that is how you define a polynomial of degree 2. So, basis is 1 x square, okay, and dimensionality or the dimension of this equal to 3. Okay. So, in this way you can calculate what are the basis vectors and you can calculate the dimensionality of any vector space, and the most important concept in this is that of linear independence. Okay. Now, actually linear independence is probably one of the most important concepts in vector spaces, and often we will be dealing with vector space of functions. Okay, and you might not take all functions, you might consider a certain class of functions, okay, and there the dimensionality need not be infinity, it can be lower than infinity. Okay. So, it is always always these ideas of linear independence, basis and dimensionality are central to many aspects, especially in quantum mechanics. Okay. So, I will stop this lecture with this. Okay. In the next class we will talk about vector operators and functions of vectors and vectors and scalar fields. Okay. Thank you.